Thank you very much, Weikong, for that introduction and the opportunity to be able to present at the BioCAT workshop. Today, I'll be sharing a very collaborative project that I have been working on as we study how the structurally defined off and on states of myosin can be decoupled from the biochemically defined SRX and DRX states. And so, as described by Weikong and others before me, the sliding filament theory is the fundamental principle behind muscle contraction and is regulated by protein interactions on both the thin and thick filaments. Briefly, thin filament regulation is significantly controlled by calcium binding. In an inhibited state, there is no calcium, and tropomyosin blocks the active myosin binding sites on actin. This means that myosin is unable to bind to actin and pull the actin filament towards the center of the sarcomere. In the presence of calcium, however, and in the activated states, calcium binds the troponin complex and transposes tropomyosin, revealing the myosin binding sites on actin. And so, coupled with this thin filament activation, there are two predominantly associated myosin mechanisms that contribute to thin filament regulation. The first is cross-bridge cycling, which starts with myosin hydrolyzing an ATP nucleotide into ADP and inorganic phosphate. This hydrolysis primes myosin and produces a weak bound interaction between myosin and actin. The release of inorganic phosphate initiates the power stroke, and myosin forms a strong binding interaction as it pulls actin towards the center of the sarcomere. During the power stroke, ADP is released, leaving myosin and actin bound in a state of rigor. The subsequent step is that a new ATP molecule binds, releasing myosin from actin, and restarting the cross-bridge cycling with ATP hydrolysis once again. The second myosin-associated regulatory of the thick filament is cross-bridge recruitment. This concept has been vigorously studied since the introduction of the SRX state by Roger Cook, where he and colleagues introduced a state of myosin ATP turnover, which is 10 times slower than the normal basal consumption rate. For the purposes of this schematic, however, we have labeled the different states of myosin as the structural off and on state, describing where the myosin heads are in proximity to actin. The population of on myosin heads are located closer in proximity to actin and readily available to interact, whereas in contrast, the off myosin heads are sequestered along the backbone and are not immediately available to bind to actin. And so with all that being said, there are currently two different techniques to study cross-bridge recruitment in muscle. The first is through structural imaging, as described with small angle X-ray diffraction. These images are able to quantify where the myosin heads are between the thick and thin filaments, along with the myosin head organization along the backbone. For the purposes of this talk, I want to visualize this equilibrium between the off and on state of myosin as a balance. As myosin transitions from one state to the other, they tilt the balance towards the larger population. And so in addition to the structural assessment, biochemical assessments through single nucleotide turnover has been utilized to quantify the ATPase rate of myosin heads. This technique and its relevance to SRX-DRX is very well described in a review published by Lehman and colleagues, stressing that these measurements quantify the percent population of myosin in each biochemically defined state, along with the associated rate constants. Again, for the purposes of this talk, I want to visualize the equilibrium of the SRX and DRX states on a balance as well. And so currently in the field, there's a general assumption that the structurally defined off and on states and the biochemically defined SRX-DRX states are correlated and or equivalent. This assumption would mean that perturbations in the structural position of myosin would directly correlate to the biochemical equilibrium and vice versa. And so, for example, if perturbations to myosin are structurally shown to increase the off state, there would be a similar shift towards the SRX state. These assumptions has generated a null hypothesis in the field, where the terms SRX and off state are used interchangeably between the two. And so, as Weikong very clearly and nicely presented earlier in his talk, a recent publication from our group and colleagues, however, has suggested that the off-on state of myosin are impacted differently by deoxy-ATP compared to the biochemical SRX-DRX state. The differences are highlighted when we focus in between the titration regions of DATP between 20% and 100%. Structurally, we see that there is no shift in the equilibrium of the off-on state within this range, and the heads remain in the same quasi-helical order conformation. However, in contrast, there's a significant decrease in the SRX state, where the population of the SRX drops all the way down to 0% and 100% ATP. And so, as described in the publication, however, a limitation to this comparison is that the biochemical experiments were done in unloaded myofibril conditions, whereas the X-ray diffraction measurements were done in loaded permeabilized tissues. In summary, however, this publication suggests that the structural off-on state of myosin may not be equivalent to the biochemical SRX-DRX states, and as this was described by Wei earlier. And so to directly test this null hypothesis, we wanted to utilize different myosin modulators to assess how cross-bridge recruitment impacts thick filament regulation in cardiac muscle. The first myosin modulator we selected was omecamtiv mecarbil, or OM. OM has been shown to inhibit inorganic phosphate release, blocking the myosin power stroke and increasing link binding interactions. OM thus has shown to prolong attachment of myosin to actin and thin filament activation, with a net effect showing that there is an increase in the number of myosin heads interacting with actin through link binding. The second myosin modulator we selected was peperin. Peperin is the primary alkali component of black pepper and has been shown to bind to the regulatory light chains of myosin. Previous work has shown that peperin depopulates the SRX state only in fast twitch scalp muscle, with no impact on slow twitch or cardiac muscle. And so, having selected our myosin modulators, we then set up our experimental design to assess how OM and peperin impacted cross-bridge recruitment and thick filament regulation in cardiac muscle. To do this, our first aim was to observe how these myosin modulators impacted the structural off-on states through X-ray diffraction imagery. The second aim was focused on the functional impact of these myosin modulators on both cross-bridge cycling and recruitment. To achieve this, we performed mechanical measurements in steady state and dynamic conditions of muscle contraction. And then finally, our third aim was to assess how these myosin modulators impacted the biochemical SRX-DRX equilibrium. By performing these experiments, we would be able to prove whether or not this null hypothesis that the on-off state and the SRX states are interchangeable, and see whether or not this is true or false. And so, going into the data with the amazing BioCAT team, we were able to collect X-ray diffraction images showing that both OM and peperin significantly altered the structural positioning of myosin. These measurements were collected from permeabilized porcine cardiac muscle bathed in relaxation solutions containing 3% dextrin. And so, initial observations of the equatorial plane shows that both OM and peperin significantly elevated the myosin heads closer to actin, increasing the on population pool. By titrating the compounds in our solutions, we were able to identify concentrations of interest, indicated by these dashed lines here, where perturbations to myosin structure were at or slightly above our designated EC50 value. For OM, this indicated concentration was 1 micromolar, and for peperin, the identified concentration was 7 micromolar. Moving to the meridional plane, we again saw that OM and peperin significantly decreased myosin head organization along the thick filament. Our first observation of interest was the intensity of myosin layer line 1, which describes the helical order of this myosin head along the backbone. And we saw that as we increase the titration of our compounds, there is a significant decrease in the intensity and the organization of the myosin heads. This is corroborated by our second observation looking at M3, which quantifies the order between this myosin head and this myosin head. And again, we see the same phenomenon, where as we increase the concentration of the compounds, we see a decrease in the intensity and the organization in the myosin, or an increase in the disorganization in the myosin heads. And finally, our observations of M6, observing the spacing of the thick filament backbone, showed that both OM and peperin significantly increased the backbone spacing and elongation. And so based on these results, OM and peperin both significantly increased the on state of myosin in cardiac tissue. Both OM significantly elevated the myosin heads closer to the thin filament. They both significantly decreased myosin head order along the thick filament, and they both significantly increased the spacing of the thick filament backbone. Relating back to our visual balance, we see that the increase in on myosin is represented by the balance leaning heavily in that direction, indicating a significant shift in the off-on equilibrium. And so next, what we wanted to investigate is how the increased on myosin state caused by OM and heparin translated to steady state and dynamic measurements of cardiac muscle contraction. And so to assess the functional impact of OM and heparin on cross-bridge cycling and recruitment, we first performed steady state mechanical measurements on permeabilized pig tissue with 3% dextrin in our solutions. This steady state assay can elucidate changes in calcium sensitivity, tension generation, myosin cooperativity, and cross-bridge cycling rate. To measure the absolute tension generated at different calcium concentrations, we performed KTRs, which quickly slack and re-stretch the muscle fibers during steady state conditions. This rapid length change allows for the myosin heads to instantly cycle off of actin, dropping the tension to zero, or regenerating the tension as myosin heads rebind to actin. And so by plotting the normalized tensions as functions of calcium concentration, we generate the traditional force PCA curves. Each compound was compared to its paired experimental control, with compound concentrations being 1 micromolar for mecamtiv and 7 micromolar for heparin. One of the most prominent differences that we saw was this elevation of tension at submaximal calcium concentrations in the presence of OM. This manifested as a significant increase in the calculated PCA50 value, where in contrast, heparin showed no statistical difference in calcium sensitivity. In addition to the altered calcium sensitivity, OM also significantly inhibited maximal tension generation, characteristic not observed in heparin. And so although less prominent than OM, heparin also expressed a slight increase in tension at submaximal force. And although there was no manifestation in the change of PCA50, both OM and heparin expressed significantly lower Hill coefficient values, or the slope of the sigmoidal relationship. And so in addition to a decrease in slope, OM and heparin both reduced the rate of tension redevelopment of myosin at maximal calcium concentrations, although as you can very clearly see that the relative reduction in cycling rate is more significant in OM compared to heparin. And so with the observed functional changes caused by OM and heparin, it is important to remember that decreased Hill coefficient values and increased calcium sensitivities are characteristics typically associated with increased on myosin head populations. What our data suggests thus is that our steady state measurements are almost validating our structural diffraction observations. And so next, what we wanted to observe is how OM and heparin impacted the activation and relaxation kinetics in myofibrils. Due to limitations of diffusion, we cannot use large strips of ventricular tissue, so we go down in the scale to myofibrils, which allows us to instantly activate myofibrils through rapid solution switching. We do this by suspending a myofibril between a motor arm and a force transducer, and with a double-barreled pipette, we can instantly expose the myofibril to high calcium, causing the myofibril to contract and allowing us to measure activation kinetics. Switching back to low calcium relaxes the myofibril and measures both the rapid relaxation kinetics shown here, as well as an initial linear phase of relaxation that measures both the rate of cross-bridge detachment, denoted by this slope, and the time of thin filament deactivation, or T-rel slope here. And so first, we observe the activation side of the measurement, and we can clearly see that OM significantly decreases the rate of myofibril activation compared to paired controls. Also, similar to what we saw in our tissue mechanics, OM significantly decreased the amount of tension generated compared to its paired control. These characteristics, however, were not shared with heparin, which had no effect on the activation kinetics as well as the force production in these cardiac myofibrils. Along with the activation kinetics, we also quantified how OM and heparin impacts the relaxation kinetics of cardiac myofibrils. We observed that both OM and heparin significantly decreased the rate of fast phase relaxation. However, similar to the KTR measurements that we saw in tissue mechanics, the relative inhibition of heparin compared to OM and K-rel slow was significantly less compared to OM. In addition to the fast phase of relaxation, we are also able to quantify how OM and heparin impacts the initial phase of slow relaxation. our measurements show that OM significantly decreased the rate of cross-bridge detachment and significantly prolonged thin filament deactivation by almost 10 times. These observations indicate that OM significantly impairs product release in cardiac myofibrils. In contrast, heparin showed no inhibition of product release, with no differences in either cross-bridge detachment rate or thin filament deactivation duration. And so these functional measurements show that both OM and heparin modulated the contractile function of cardiac muscle, although the relative magnitude of impact was greatly significant in OM compared to heparin. We observed that both OM and heparin decreased cardiac cooperativity and KTR in cardiac tissues, as well as decreased the rate of fast myofibril relaxation. However, only OM showed the phenotypes that were associated with decreased force in cardiac stripped myofibrils, an increase in calcium sensitivity, inhibited myofibril activation, and inhibited thin filament deactivation and cross-bridge detachment, thus alluding to inhibited product release. And so even though OM and heparin showed similar on and off equilibrium transitions, heparin had a significantly blunted impact on contractile dysregulation compared to OM. And so the significant impact of OM could potentially be tied to the complexity of the compound's mechanistic alterations in myosin. These results show that heparin is cleaner and less intrusive myosin modulator when attempting to alter the on-off states without significantly impacting contractile function. With that said, our next goal was to observe how these myosin modulators impacted the SRX and DRX equilibrium in permeabilized single cardiomyocytes. An important reminder is that previous heparin studies showed that myosin modulated only impacted the SRX, DRX populations in the fast skeletal muscle. So again, only heparin impacted the fast skeletal muscle population while having no impact on slow twitch and cardiac muscle. And so to conduct these single nucleotide turnover experiments to assess how OM and heparin impacts the SRX-DRX equilibrium, we worked with our collaborator, Vivek from Johns Hopkins. Vivek has constructed his own single monocyte turnover ring, which allows him to measure the fluorescent turnover of manned ATP in a loaded cardiomyocyte for an observation period of approximately 1,000 seconds. Experimental cardiomyocytes first undergo a controlled turnover run to serve as the paired control before being washed in Riger solution and then reloaded with manned ATP in the presence of the compound and then rerun for the nucleotide turnover. These measurements are significantly arduous, and although we have not been able to collect the complete data set just yet, we wanted to share our initial findings and results. And so initial results quantifying the percent SRX population showed that both OM and heparin did not significantly impact the SRX-DRX equilibrium. These findings for heparin are consistent with what is found in the literature again. And then in addition to the percent SRX populations, we also quantified the T1 and T2 time constants. However, due to the current spread and the initial results, we want to wait and increase our statistical power before making any conclusions about these turnover kinetics. And so by running these single nucleotide turnover assays, our initial results suggest that OM and heparin have no impact on the equilibrium of the SRX-DRX state. These turnovers results suggest, and are in contrast with the structural X-ray diffraction measurements, it suggests that the structural off-on state is not interchangeable with the SRX-DRX state. These results suggest that the null hypothesis is false, and that the off state and the SRX state are not interchangeable since they do not describe a similar and equivalent phenomenon. And so with these findings in mind, we hope to discuss how to best decouple the on-off state from the SRX state, since they can quantify significantly different components of myosin cross-bridge recruitment. What our data suggests is that the position of the myosin head is independent from nucleotide cycling dynamics, and that the off-on designation should be the preferred labeling term when discussing myosin head position when you compare it between the thin and thick filaments. And so with that, I really want to thank all of the collaborators that have worked on this project. We couldn't have done everything without everybody's assistance and expertise. And also I want to thank again Weikong for all of his assistance and work on this project as well as the funding opportunities. And my base here at UW with the Rainier Lab wouldn't have picked a better lab. Thank you.
Thanks. Any questions from the audience? You can go ahead, unmute yourself, and ask the speaker directly.
I have a question. Saffie, can you hear me?
Have you muted?
Yes, sir, yes.
Yeah, just a little provocative question. It's very nice work. Thank you very much. I appreciate it a lot. But could it be also that biochemical measurements could be not of the same resolution and rigor maybe, or as mechanical and structural data? Could it arise also from some, I don't know, problems in the biochemical way to assess the SRX-DRX ratio? It seems to me that let's say the type of results that you get from structural and from mechanical is much higher as a confidence interval that you have compared to biochemistry. So we have to look for a more precise and maybe alternative way to estimate the SRX-DRX state that for sure exists. Okay.
Yes, I personally agree with that sentiment. So we have a stop flow rig in our assay, and we've been trying to optimize that rig. And I know Bert as well has also been trying to optimize stuff. There's several labs trying to optimize this calculation. And I think right now in the field, and the way that Mike Jeeves, who we've been working with, trying to understand these population states between SRX and DRX, I completely agree that currently the way that these are being analyzed, the resolution, though, is good and potentially shows shifts in these equilibrium populations, is not as high of a resolution as you were saying, as what we can decipher from these mechanical and from these specifically X-ray diffraction, which is on a resolution up to itself with how well the diffraction images can be. And so I think the biggest purpose of this talk and the project that we're looking at is that although SRX and DRX is truly a phenomenon, nobody's doubting that it doesn't exist. It truly does exist. I think from a labeling perspective, because we as scientists want to label things, it is easier to label it with the higher resolution, the higher quantification of the X-ray diffraction before kind of trying to go into this turnover, I want to say like Pandora's box, because we really don't know exactly what's going on. There's a lot of different reviews that are also observing and seeing that in S2 or S1 isolations, mavacamten still slows down those rates. And so that is unable to obviously hold back and form an interacting Hess motif. And what we've seen is that mavacamten personally in our hands in our lab does decrease that rate. And so there's still so much that needs to be understood about this shift between SRX and DRX that I don't want to say it's safer, but it's a higher resolution and a higher finite clarification if we label these transitions, especially in the position when we're talking about the position of the myosin heads with the on-off designation. But yes, I completely agree with your statement. Yes, Mike.
Hi. I'm sorry. Was somebody else going to talk?
Yeah, I just like to comment a little bit on that one. If you look cardiac muscle, the process is relatively fast, and going to SRX state probably will be very slow process. We rather should define, as you guys found, on and off states, because one is fast and probably probable, another one is slow, like it's smooth muscle, where you have time to form these kind of different states is more possible. This is just my comment.
So I like the way that Chiara raised this, in that the resolution of sort of the stop flow types of measurements or any other types of preparations where you're looking at these distinct ATPases and which group is affected. It's fairly low resolution. And that's fine, I think, but what it brings up the point is that we need to be aware constantly of the limitations of each of these techniques. And just because it's relatively more simple to use, it can't explain everything. However, I would caution that X-ray diffraction and that myofibril kinetics is also an average. of what myosins are doing. And so we need to also realize the limitations of that as well. And I think that it's having the combination of all of these approaches to attack the problems and seeing where there are similarities and differences is very, very valuable. So that's where I see the value of this study, is it's showing us that we need to, look more deeply or think more deeply, and we can't preliminarily just sort of, conclude, one thing that's going along with what our current thoughts are. The other thing I would say is the thing to add to this is more detailed structure. So X-ray diffraction is great for detail in terms of a thick filament or set of thick filaments. But I think really the protein structure is going to give additional hints in this. And I know that we have the structure of omecamtiv mecarbil. I think Anne is on right now, and she's done that. But I don't think peperin has been looked at, right? We don't know the binding site for that specifically.
It's just a suggested IRC.
Yeah,
other than a past RLC.
Really, I think what it is looking, as we grow our data sets, sort of looking for what are the common and uncommon features and changes of structure that cause similar physiological types of events to occur. So that's my soapbox. I'll step back down now.
I agree with what has been said by all of you right now, and I thank you for all the presentation. I really enjoyed the meeting, and I think that it's because we are looking at effects of drugs on the cycle as well in the equilibrium. So it's not as simple as, and I think that's why indeed the structures can help with understanding more detail on what is going on during force production, as well as in the cycle, as well as in the equilibrium. So all of it is important, and indeed the time scale of the equilibrium is different. So that's why it's not so easy to know what each drug does, but it's quite interesting to know what the myosin can do. And one is with the thick filament and everything around, and the other one no. So all of that explains the differences. Yeah, for me. Thank you. That was my comment.